magnetic monopole. So let's get started. So we know that the Gauss law for the magnetic field is this, right? And this is equivalent to that. So it means that the resulting flux through any closed surface is zero. Now, so next is, what do we mean by a magnetic monopole? So it is an object which gives you this field, and then you see that if you plug this field into this equation and then you evaluate this closed surface integral where we have a monopole inside it, you see that it gives you a non-zero. So it is the case that the magnetic monopole can't exist according to the Gauss's law. But actually the first equation just gives us another way to characterize the magnetic field. So we can write the magnetic field in this form, and it means that if we can find a function A, and then we take the curl, if you get any B, then it's going to be sort of a physical magnetic field that's possible. And now I'm going to construct the A that gives you nearly exactly this field, which is this. So we're going to need to take the curl in the polar coordinate, and it can be easily done using this identity. Okay, so there is that. Right. So I'm going to assume that our vector potential has only the phi direction. And you see that according to this, if our A has only phi direction, this integral over the surface, which is a surface of constant phi, will be zero, right? And by this equation, it tells you that the curl of A in the phi direction is zero. And okay, so that's one component done. The other component is this thing. This is the surface of constant theta. And then if you do the same calculation, you compute this thing, you will get minus that's the curve in the theta direction. And you'll see that if you want this magnetic field in the theta direction to be zero, you want this to be zero, which means that actually this field is that. Right? Now, the last part is this surface, which is the surface constant r. So the curl is that's the curl in the r direction. And then we see that if we want to get the r squared, inverse r squared here, we just need to we just want this thing to be minus cos theta, right? Which means that this is minus cos theta over r sine theta. And then you see that when you take the curl, it will give you the ratio component which has inverse r squared law. Now, you might already see that this A has a a bit of a problem because we have a singularity whenever the sine theta is 0, which means that the whole z-axis is a singularity. Now we actually can get rid of half of them by just add one here, because that doesn't change the partial derivative there. And that gets rid of the singularity over the plus z direction. And now we have the singularity on the minus z axis. And that's crucial. I mean, that's, it has to be that, because these three characterizations are equivalent. And these things say you cannot have that. So it means that even if you write it in this form, you have to end up with something which is not regular anymore, which is, I mean, which has to have some singularity somewhere. And so the next part is we're going to understand what is actually this singularity. So the next part is going to be what's mainly due to Dirac's idea. So let's consider a solenoid infinitely long, semi-infinitely long, and let's say that the current is flowing in this way, in this direction. Now, I claim that if you compute the field, the magnetic field from this solenoid, you will get exactly this field. And it is because if we assume that the solenoid is small enough, and if we slice this in this way, and then you see that this ring, this part of the solenoid, is actually a magnetic dipole, right? It's just like a current loop, so it's a magnetic dipole. But now we know exactly the field produced by this magnetic dipole, and that field is this. Right? Okay, so what we need to do now is we need to integrate the field, this equation, and then you will see that the field far away from this solenoid is going to be point-like. And so I'm going to integrate this actually by explanation. So I claim that if you replace this magnetic dipole moment here with the electric dipole moment, and you change this mu naught to 1 over epsilon naught, what you will get is you will get an electric field from dipole. And we know exactly the solution for the electric case, right? In the electric case, if you have a dipole which has a constant constant electric moment density here, you know that it's going to be of this form. So on. Right? And the charge here, I mean the magnitude of the charge here has to be equal so that you keep the constant of the dipole moment. And so you see that in the electric case, this thing cancels, right? So what you're left with is this plus charge and minus at infinity. And so you know that if you integrate this, what you will end up with is a monopole field everywhere except on the solenoid. Right? So we know that if we integrate this,